Let's consider this satellite question, okay, a satellite motion question. We have a, say this is the situation. This is an asteroid, okay, and we have a man-made satellite orbiting around that asteroid, taking pictures of it, say. And the mass of the asteroid is 10 to the 6 kilograms, or 1,000,000 kilograms, or 1,000 tons, and the mass of the orbiter is 500 kilograms, okay? And we're saying that it is orbiting at a radius of 2,000 meters, okay? So it's 2,000 meters from the center of the asteroid. Remember, it's the distance from the center, so I should draw that like that, there, that is the important distance. Okay, if you're given the altitude, the distance above the surface, you need to add it to the radius of the asteroid to find out the distance from the center. So, what kinds of things are we likely to be asked to find in this question? Okay, we might be asked to find the period of the orbit, okay, or we might be asked to find the orbital speed, something like that. So let's start by trying to find the orbital speed. How do we go about doing this? Well, for us, this combines two different ideas, okay? It combines circular motion and the laws of gravitation. Circular motion from the point of view that, all right, we're going around a circle, and laws of gravitation from the point of view of, well, we have to find out what is the force of gravity acting from the asteroid on that satellite. So, how do we do this? If we want to find the orbital speed, what equations are we likely to use? Well, I said circular motion, so we're probably going to be using A equals V squared over R, or F centripetal force equals mv squared over R. Something like that. And it's a satellite question, so it's almost certain that we're going to be using one of these equations. We could be using G equals Gm on R squared, okay, where G is the universal gravitational constant. G equals 6.67 times 10 to the minus 11, okay. So we could be using this one, or we could be using F, G, gravitational force, equals G m1 m2 over R squared. Okay, so those are some related equations. Now, these two equations work together, okay, because this G, and we've used it in, F equals mg, we've used this G symbol to represent the acceleration due to gravity. So that's just the acceleration due to gravity, okay, and this is an acceleration here. So these two equations work together, and these two equations are both about force, so these two work together as well. These equations are slightly simpler, so I'm going to use these. And if we were trying to find the orbital speed, we would actually find that these masses cancelled out, and we wound up with these same formulas anyway, okay? So, let's just go with these equations. Okay, A equals V squared on R, G, the acceleration due to gravity, equals Gm on R squared. So when we're out here, in this satellite orbiting around this asteroid, the acceleration is always towards the centre, okay, because that's how circular motion works, and the acceleration is given by the acceleration due to gravity, because there are no other forces acting on it out there. So we can set these two things equal, because the acceleration in the circular motion is equal to the acceleration due to gravity. So we can say V squared on R equals Gm on R squared. Which m is this? This is the mass of the object at the centre, okay? We always use the mass of the object at the centre. We know that the mass of the object doing the orbiting is irrelevant to these kinds of questions. You know that in a vacuum, a pebble and a bowling ball will fall at exactly the same rate. They'll accelerate at exactly the same rate, okay? That means that this acceleration is independent of the mass of the bowling ball. It's only dependent on the mass of the Earth. So now that we've set these two things equal, we just need to rearrange to try and find V, and we can multiply the R across. and we can square root both sides to get v on its own. So we'll end up with v equals the square root of g m r on r squared. I've multiplied the r across and I square rooted, but we've got an r on the top and an r on the bottom, so it's just going to be gm on r. Okay, those are going to cancel out. One of the r's on the bottom cancels out because that was squared. And if I just plug the numbers into the equation now, I'll find the orbital velocity. I've got to plug in the mass of the satellite, which is 10 to the 6. So I've got to plug in g, which is 6.67 times 10 to the minus 11. So 6.67 times 10 to the minus 11 times the mass, which is 10 to the 6. So times 10 to the 6 over 2,000. Okay, and I'm going to get the square root of, so some of these thousands and so on are going to cancel out. I'm going to get 6.67 times 10 to the minus. Now, 10 to the 6 times 10 to the minus 11 will get you 10 to the minus 5. Okay, because we add these two indices together when we're multiplying things with the same base. And I'm dividing, let's say that that's 2 times 1,000 on the bottom there, so I'm dividing by another 10 to the 3. So when I combine all of those indices, I end up with 10 to the minus 8. Okay? And doing the square root over 2. I took out a factor of 1,000 and moved it up to the top. So that's going to be 3.3 square root of 3.33 times 10 to the minus 8. And you can plug that into your calculator and work what that output that is equal to. It's actually going to be an incredibly small velocity. Okay, it's going to be a really, really small number for the velocity because the force of gravity between these two things is actually going to be incredibly weak. That means that there's a very, very small centripetal force, and the smaller the centripetal force, the smaller your velocity has to be in order to go to complete that circle of that radius. Think about it in terms of if you're going around a roundabout in your car. If it's an icy road, you have to go at a smaller speed because the road can't provide enough frictional force to push you towards the centre for you to go around that at a high speed. Okay? Similar thing here, because we've got a small centripetal force from gravity, you can only orbit at a very slow speed.